Thank you very much. I'd like to thank the organizers for the opportunity to speak. I'd like to thank the people from Recovering from Karaoke who made it into the talk this morning. I hope karaoke went well. Before I go to my first slide, I'm going to take a slight deviation from mathematics to explain what the next slide is about. So today in Canada is National Indigenous Peoples Day. It's a day to celebrate history, heritage, resilience, and diversity of the First Nations, Inuit, and Métis people across Canada. And to some extent, if we want good allies, we have to be good allies. So I want to explain some of what's going on here, because the next one is going to be the territorial acknowledgement for my university. But I want to give a bit of background, especially for people who are not in Canada. So in 2007, there was the Indigenous Residential Schools Settlement. This was the largest class action settlement from Canada. And as a result of this, there was a Truth and Reconciliation Commission set up from 2007 to 2015, and it documented huge numbers of cases of stories of survivors. I am not Indigenous. These are not my stories to tell. These stories are very, very well documented on the Truth and Reconciliation Commission's website. And as a result of this Truth and Reconciliation, there was 94 calls to action. One of the calls to action was that before events such as this, we have a territorial acknowledgement. We did have one at the beginning that talked about the territorial acknowledgement of where this campus is settled. Waterloo is a different territory. So the University of Waterloo acknowledges much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee people. The main campus is situated on the Haldeman Tract, a land granted to the Six Nations that includes 6 miles on either side of the Grand River. There's active work of reconciliation takes place all the campuses and research, learning, and teaching, and is coordinated through the Office of Indigenous Relations. So this comment about 6 miles on either side of the Grand River, the University of Waterloo is 3.5 miles from the Grand River. So we're not like on the border. We are firmly inside the land that was given to the Haudenosaunee people as a result of fighting those pesky Americans during the American Revolution. They lost their lives, lost their land, and they used to be living in upper state New York. This is the land granted to them. Nowadays, they have about 10% of the land that was granted to them. Now, onto the talk. So, inspired by all the flash talks, this is more 6 flash talks, all with the same theme and with no changeover of speakers. And no gong, don't use the gong. So the theme is very, very firmly on the number theory side. So far away, it can't see algebraic geometry. Sorry, it's number theory. So I'm going to start with a simple example. I have to have 2 pi in here somewhere, so this is the pi part. So pi, we can represent pi in base 10. This is something we've all done. And we always think of it as sort of a digit times the power of 10. And then another digit times the power of 10, then another digit times the power of 10. And this is the typical way we represent numbers. In this case, we have the digits are 0 through 9, the base is 10, and we have the integer part, which is everything before the decimal point. So in this case, it's 3. And we have the fractional part, which is everything after the decimal point. So this is 0.1415926, da, 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 da. And historically, lots of other bases have been used. So base 2, I mean, this is computers. That's what this computer is actually is probably using base 16 or something. But base 2 was traditionally computers. There's an interesting system set up at Moscow State University where there's a base 3 representation and it used digits 0, 1, and -1. And it was a classic example of bureaucracy versus research, because they kept creating it, then getting shut down because the bureaucrats didn't like it, then creating it, then getting it shut down. That base 5 was used by a number of the indigenous groups of Australia, Western Africa. Base 8, I like this one. They based on base 8 based on the spaces between the fingers. This is where they got the base 8 idea from. 10 tends to be what we use now. There's an 11 in here, which it's a story I read on the internet, so it must be true. During the French Revolution, I mean, among other things, one of the things they're debating about is moving to the decimal system from what was sort of a base 12 system then. And people said, well, let's compromise. Let's use base 11. Thank God no one compromised on that. Base 15, 20, the Babylonians were actually a mixed base system with 6s and 10s. But there's lots of bases used historically. So if we've got, I'm going to say we've got a D, or one of these representations where D is the base and script B, sorry, gay D is the set of digits. And this is how we would represent something. And historically, little d has always been a natural number, and gay d has been the digits from 0 to d minus 1. D doesn't have to be a natural number. It doesn't have to be 2, 3, 4. It can be negative. It can be a real number. You could use things base pi. You could use a complex number. You can use matrices. The set of digits doesn't have to be a subset of the integers. Again, you could use vectors. You could use complex numbers. You can use any sort of stuff. And then you can still talk about, well, what do you have with the integers representations? What do you have with the fractional representations? And there's a lot of sort of overlying themes of these questions. But one of the comments I didn't put in here, I probably should have is, so first one, when can everything be represented? When can everything be represented uniquely? Because sometimes you have things that have, like even base 10, 1 has 2 representations. You've got 1 and 0.999. If I used a different base, I might get 6 representations for 1, or I might get an infinite number of representations of 1. I can do some crazy stuff here. So when do I have unique representations? What does the topology of the integer parts look like? Or what does the topology of the fractional parts look like? It's not always as nicely structured as you think, and sometimes you get some really nice fractally type objects. If it's not unique, how non-unique can it be? Can this be quantified? And are there applications to this? In some cases, well, in most cases for me, no, because I do things because I think they're fun. But some of them accidentally had applications. So I should actually comment, not all of these topics are things that I've worked on. Some of these are very classical, historical. Some of them are just good examples. Some of them are things that I've worked on. So this is not something I've actually worked on, but it's sort of an interesting example. So instead of base 2 or base 3, use base 4/3. Turns out everything I think of as a traditional integer can be represented with this base. But there are things that are represented this base as integers in this base that are not traditional integers. For example, 1, 0 would represent 4/3. So I'm definitely representing more. So all the traditional integers can be represented, but we're representing more than the traditional integers. So as an example here, I've listed the first 29 integers in base 10, and then I've written it in base 4/3. We see the base 4/3 examples are much longer, but it's one of the questions we're sort of curious about is, like, how do we get this, and is there a good constructive way? Why do we get all the integers? So I'm going to do a proof, but this is probably the only real proof in it, and it's not very hard. Yep. Okay, you answered your own question? Perfect, I like those. So I'm going to consider this map T, where it takes an integer, a traditional base 10 integer x, and subtracts off what I'm going to call the good digit and divide by the base. This is really what I'm doing is if I'm looking at what I hope is the base 4/3 representation, I'm trying to figure out what the last digit is, remove it, and then shift everything over and then repeat. In this case, my definition of good digit will be 0 if x is 0 mod 4, 1 if it's 1 mod 4, and so on. And what this does is it takes our base 4/3 representation, figures out what A0 is, removes it, shifts it over, and gets a smaller thing that I'm trying to represent. So let's see how this would work for 17. Well, it's 17, we've got, oh, that's crazy. 17, we've got a good digit, which is 1, because it's 1 mod 4. I'm going to move that hand out of the way, because it's driving me crazy. and divide 16 by 4/3, I get 12. And I just keep going. And if I read these digits upwards, 32101, I get 32101. That is my base 4/3 representation. So the takeaway from this is working backwards is useful to determine the digits. Yeah. Sorry? Yeah. There's nothing deep here. I'm a very, very shallow mathematician. I've been told that a lot about particular Hollywood actors. I'm very shallow. Anyways, yeah, I'm just looking at basically trying to figure out what this last digit is. So I'm sort of looking at what the residue class of it is that it's lying in, and then just shifting everything over, say, well, I figured out A0, I can move on. So that's all I'm doing. So takeaway, working backwards is useful. And second comment is having enough good digits is useful. Because if I didn't have 0, 1, 2, and 3, I would not be able to do this. I need enough digits to get this to work. So let's look at an example, moving beyond the rationals to a complex space. And this is a very, very classic example for people who study almost any first course in fractal geometry is going to deal with this example. So I've got two different bases here. They look very, very similar. They're going to have very different properties. One of them is -1 plus I. The other one is 1 plus I. The digits are 0 and 1. The nice thing about these two bases is, well, in one of the cases, we can actually represent every Gaussian integer this way. If as an integer in this base, we can actually represent, if we go to the fractional parts, we can represent everything in the complex numbers this way. For the other base, we get half of the set. So what can we say about the representations of the numbers? And as before, we can work backwards to try to get this. So we have their same function as before. X goes to x minus a good digit, and you divide by the base. And for Gaussian integers, my definition of good digit is it's going to be 0 if a is congruent to b mod 2, where I'm trying to represent a plus bi, or 1 if a is not congruent to b mod 2. And I choose it in this, yep. What's really happening here is you're choosing the good digits so that when you say a plus bi minus a good digit and do the division, you stay as a Gaussian integer. So you're actually looking at residue classes. Yeah. So let's look at two examples, and so I'm going to try to represent 2 minus I. So in the first case, I look at 2 minus I. I say, well, 2 and minus 1, they're not the same, so my good digit is going to be 1. So I look at 2 minus I minus 1, and then I divide that by minus 1 plus I, and the result is minus 1. And then I say, well, minus 1, that's really minus 1 plus 0i. They're different. My good digit is 1. So I subtract off 1 from that, so I actually have minus 2, and now I divide that by minus 1 plus I. And I just keep going, and at some point, I'm done. I get a 0. I've got a representation. So the representation reading backwards of 1, 1, 1, 0, 1, 1 is my representation base minus 1 plus I. No, because the second case doesn't terminate. In the second case, if I try to do the same process, I get this I here, and then I subtract off the good digit of 1, I get an I. You subtract off the good digit of 1, get an I. If I try to represent it, I'm sort of got like reading backwards from least significant to most significant, 1, 1, 0, 1, or sorry, 1, 1, 1, 0, and then it's a whole sequence of ones, which is not good. You're not representing everything. Sorry? Pi would be right. Well, you always have to decide on what your digits are and what your base is. Base 10, 0 to 9. You could represent that if you go into the fractional part. In this case, I was sticking for something that looked like integers. But yeah, yeah. Although this actually, in base 10, you can represent 3 quite easily. You cannot represent -3 in base 10 if you tried to do this process because you need that extra sign digit. But in base 10, this would be a weird thing to do, but you could do it. If you use base 10 and digits -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, you could represent -3. It would be -10 plus 7 or something like that. So you can do some strange things. So what do the fractional parts of this look like? And this is a picture that so many people see in fractal jump. That is a fractional part. That is sort of the equivalent of the unit interval if I was looking at base 10 and 0 to 9. Doesn't look like an interval. That is the equivalent of the unit interval. And they look, and this is for D1. So this is the thing where it actually turns out you can represent everything. This is D2. It looks, this is the one where you can't represent anything, but you look at the two pictures and say, those look the same. What's going on here? So let's look at, instead of looking at the fractional part, I'm going to look at all possible representations. I'm going to say, and I'm going to have the fractional part. Actually, I'll just show the picture. I had to redo these so it has a proper rainbow fractal. So this here, that is sort of the equivalent to the unit interval. It's starting with 0 and point da 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 da. The orange here, that's starting with 1 point da 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 da. The yellow is starting with 1 something point da 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 da, and I just keep going. And this actually covers the entire complex plane. If, on the other hand, I use the D2, I actually get this, it's a spiral that goes all the way out, a beautiful rainbow spiral, but it's missing half of the complex numbers in some sense. So it's really interesting that all I'm changing was -1 plus I to 1 plus I, and the whole what you can represent, what you can't, changed drastically. So what I want is all the equivalent of a unit interval. So I want 0.1 or 0 or 1, 0, 1, 0, 1, like all of those things. And that is the red part here. That is all the things that start with a 0 and have stuff after the decimal point. And this red part starts with a 0, everything after the decimal point. This is a dragon curve, yeah. So take away from this, it turns out all the Gaussian integers can be represented if it was -1 plus I, but only half of them could be if it was +1 plus I. All of C can be represented if it's -1 plus I, if I just go to all the fractional bases, but you only get sort of half of them if it's the 1 plus I. So take away from this is sometimes having enough digits isn't enough. Sometimes you're still going to miss stuff because you somehow don't capture half of the object or some portion of the object. Yeah, just stretching. Okay. Next flash talk, too many digits. So question is, what happens if I have too many digits? So base 2, something we've seen before, but instead of using digits 0 and 1, so typical binary, I'm going to use the digits 0, 1, 2, 3, 4, 5, 6. Like, it seems like a weird thing to do, but you've got lots and lots of representations. And in fact, for example, if I want to represent 6, well, I could represent 6 as just 6. That's easy. Or I could use it as 114 because it's 1 times 2 plus 4, or 2, 2, or 3, 0, or turns out there's 6 representations in this case. So one of the questions we asked is, we made a definition saying, let's say I've got a base D, digits 0 through Q minus 1. I'm going to define this function to be the number of representations. And I'm probably not going to use this function much. It's more just think of it, I'm trying to count how many times am I over-representing and how does this grow as n goes up. So very, very simple example. I'm going to slowly increase the size of the digit set. So the first example, base 3, digits 0. You can't represent anything. Well, you can represent 0, nothing else. Base 3, digits 0 and 1. you can sort of see it here that you can represent some stuff, but most of the stuff you're not representing. And this is actually sort of like a Cantor set in reverse. You've got these gaps that are increasing, but it's very Cantor-like in its shape. Base 3, digits 0, 1, and 2, you can represent all the integers uniquely. Well, if you're using integer representations. Base 3, digits 0, 1, 2, and 3, you start seeing some growth patterns. You start seeing some things that have more representations. Base 3, digits 0 through 4. Again, you have some things that are growing, and you're starting to get more and more representations. Next one's interesting. I mean, all of these, it looks sort of scattery. You've got some stuff that seems to be high, some stuff that seems to be low. Base 3, digits 0 through 5. Something's going on there. It's not scattered anymore. 0 through 6, you've got some scattering. 0 through 7, you've got some scattering. 0 through 8, that's stupidly easy to describe. I know what that function is. And things sort of grow, but we see that when it's, in this case, 0 through 8, you've got a 9 there. When 3 is dividing 9, something's nice happening. When 3 divides 6, something nice happens. When 3 doesn't divide the number, I've sort of got an upper bound and lower bound, but it's not as clear-cut what's going on. Something like that. I know a variation of this anyways showed up on a Putnam at one point. I could figure it out. It's probably something like 1/3. But yeah. But yeah, something like that. So if Q's less than D, then numbers have at most one representation. That was sort of a Cantor-like thing at the beginning. If Q equals D, we had a unique representation. If Q is greater than D, we potentially have more than one representation. If D divides Q, something nice is going on. So one of the questions we looked at was, what can we say about these asymptotics? And how fast does it grow on average, at worst, at best? And so, I mean, if we have something like this is 3 in digits 0 through 19. What I really want to figure out was what sort of the upper bound is looking like and what is the lower bound looking like. And this was studied by Protasov in 2000, where he was looking only at base 2. And he did have a conjecture of how things worked and proved it for a small number of cases using incredibly hard techniques. And in particular, if Q was 3, 5, or 9, it was one case, and if it was 7, 11, or 13, it was another case. It was this weird thing where it's like, it's the maximum of these things for the upper bound growth and the lower of these things for the lower bound growth, and these relate to things called the joint spectral radius or the lower spectral radius of a set of matrices, which have an interesting history and research in their own right. This was his conjecture, and I'm going to relate this to something else because it's going to explain what actually is happening. So if I write 3 in base 2, it's 1, 1. If I add up all those digits, it's 1 plus 1, so it's 2. If I write 5 in base 3, it's 1, 0, 1. Add up those digits, 1 plus 0 plus 1, I've got 2. And I can keep doing this. And I said, well, in 3, 5, and 9, it's 2. In 3, 5, and 9, the upper bound is given by this square root. In 7, 11, and 13, it's 3. And in 7, 11, and 13, the lower bound is given by the square root. There's a pattern here. Using different techniques and process, I really extended this data. We actually went out to like 100 or 200 or something, but really extended it, and you can really see the pattern showing up. If you add up all the binary digits and it's even, it looks like the upper bound's coming from the square root. You add up all the digits and it's odd, the lower bound's coming from the square root. And turns out this doesn't necessarily, there's something like this also happening if it's base 3 or base 4. So something is going on here. Oh, I'm glossing over that. They are explicitly computable matrices that I am in no way going to describe. They are coming from the fact that this is a 2 regular sequence, and most of these things can be constructed using a matrix representation. I really don't want to describe them. Right. Yeah, and really rows should be the maximum joint spectral radius, but it turns out in this case it simplifies to one of those two things. The theorem is, here's the 6 cases he managed to prove. So we proved about 100 cases because it made the data a lot more obvious. Okay, and turns out, I mean, this is what we're conjecturing, and we actually have I guess I have a conjecture that's way more detailed than this, but this is sort of what's happening if I have too many digits. Next flash talk where I get to pretend to be an engineer. So I'm going to give a bit of history about quasicrystals. On Wednesday, we had a description of where physics was useful for something. Unlike the speaker on Wednesday, I don't understand the physics, but I can give some history of quasicrystals. So crystals have been studied for a long time, and they have these nice rotational symmetries. They tend to be rotational symmetries of 4 or 6, and that's it. And in fact, you can prove this mathematically because crystals have some very nice lattice-type structures. If you have a rotational symmetry in a lattice, that's basically it. And there's a long study of just taking lasers, shooting it at crystals, and looking at the diffraction patterns, because light is sort of a wave, and then looking at the peaks of those diffraction patterns and saying something about the crystal. Back in, I think it was 84, they did this for this one crystal-y thing, and they got a diffraction pattern that looked like it had a rotational symmetry of 5. And they're going, WTF, that does not make sense. So they spent the next 2 years trying to figure out where the mistake was and how you could possibly rotate a cube in just the right way to get a symmetry of 5. And they finally acknowledged it wasn't going to happen. They had found something new. And that is a quasicrystal. So it started in 84 and now has applications to nonstick frying pans, which I do not understand. But since it has applications to material construction, I consider myself an engineer. Okay, so one way to model these, I'm again going to use a digit and a set of bases, or sorry, a set of digits and a base. The base is going to be the golden ratio. And the digits are going to be 0 plus the 5th root of unity. And I just want to look at all the integers given these digit set and given this base. That is a set of integers. I think I went minus 10 to 10 on the real line, minus 10 to 10 on the imaginary axis. And you can sort of see some patterns here. In a lot of cases, if you choose the base in this way, you don't get a nice pattern. You don't get these sort of circly objects. You actually get things that get denser and denser as you get further out. So the fact this has structure at all is somewhat surprising. And there's this process called tiling where you take 2 points, you look at the sort of line that goes between them that's equidistant to all these points, and you can construct a tiling based on these points. I want to show the tiling. I'll skip that. That is what the tiling looks like, which is just pretty. And I think one of those, it would be perfect for Zen doodles. Just give it a blank one and tell you to color it in. Yeah, that's exactly it. I was just not quite remembering the word for it. So some of the math, so a lattice has some nice properties. If you take a lattice, you subtract off the lattice itself, you stay in the lattice. A quasi-lattice, which is what quasicrystals are based on, have the property that if you take the lattice, subtract off a lattice, you're contained within the lattice plus some finite set. So you're sort of lattice-like, but not completely lattice. And for theoretical reasons, they always get dependent upon piezocyclotomic numbers, which I have not, well, I guess I did define. So piezocyclotomic number is some algebraic integer. All of the algebraic integers conjugates are strictly less than 1 in absolute value, and it generates the same ring as z adjoined 2 cos 2 pi over n. So that's the piezocyclotomic number of order n, and the order actually deals with the rotational symmetry. So a bunch of results in this. Some work I did a long time ago on my postdoc was sort of a classification for degree 3, 2, 3, and 4. Once you get beyond that, although in theory they're quasi-lattices and quasi-crystals, they look so chaotic, I don't think you'd ever see it experimentally. It just wouldn't show up in the Bragg-Peets. And then there's some criteria for constructing quasi-crystals in this way. This is not the standard way to construct them, but it works. So golden ratio, 0 in the 5th roots of unity. You can color in the tiling, and certain things just show up over and over and over again. And you just see a lot of patterns there. Base golden ratio, 0 in the 10th roots of unity. Again, lots and lots of patterns showing up. It feels sort of crystal-like, or crystal, except this rotational symmetries are wrong for a crystal. So everything that's red has the exact same shape. Everything that's green has the exact same shape. The fact I chose red was for random number generator. I just randomly chose colors until it looked good. But it was the criteria that I wanted everything the same shape to the same color. And you can sort of see that all the little yellow ones are little sort of diamonds. And the red ones are different shaped diamonds. I allowed rotation in this, but nothing else. Golden ratio squared in the 10th roots of unity, I get a different pattern. So these are rotational symmetries of 5 or 10. You could also get rotational symmetries of 8. I like this one. And again, I did the coloring based on everything the same shape had the same color. And this is why you don't go much further, although it's a pretty picture. I wouldn't recognize that as a crystal or having enough structure to be a crystal. And it gets crazier the higher dimension, or the higher sort of things you go. Sorry?
What is kappa?
I have no idea. I'd have to look this up.
But it's some algebraic number.
It's an algebraic integer. It's a piezocyclotomic number of some sort, probably with a rotational symmetry of 12. So possibly, my guess is degree 3, but I can't remember the exact details. It is a quasi-crystal. There actually are a finite number of tiles, but the finite number is like 1,000 different types of tiles. So not a useful quasi-crystal. Whereas this, there's a finite number of tiles, and there's 1, 2, 3, 4 of them really. It's not that many, so it feels more crystal-y. I mean, this is a vague sort of description of what is and isn't it. I mean, both of them are quasi-crystals. That's one you'd actually be able to recognize from these lasers experimentally. That one you're never going to see. And really, these things are more three-dimensional than this. But drawing these things three-dimensional is going to be really annoying. So it's two-dimensional. And really, it was an excuse to draw pretty pictures. Okay. Next, this some other examples. Matrix bases. Part 1, this is not stuff I've done, but it's a very classical area. It's like, use a matrix base, and I'm going to call it an expansive matrix if all the eigenvalues are strictly greater than 1. And it turns out you can represent, if you choose your vectors right, like vectors 0, 1, 0, -1, maybe a few other things. If you do this right, you can represent sort of a lattice structure based on this matrix. So that the integer parts. You could, if you nice thing about expansive matrices, if I invert the matrix, because all the eigenvalues were originally greater than 1, all the eigenvalues of the inverse are -1. So if I start looking through the fractional parts, I am going to start filling stuff in. So in this particular example, if I chose this digit set of size 5, turns out I could represent everything in the lattice with this base and with this digit set. And if I go to the fractional part, I'm going to get everything. And just like before, we actually use the same moving backwards function. You take a vector, you figure out what a good digit is, and really the property of good digit is if you take a vector and subtract the good digit and multiply it by the inverse of the matrix, you stay an integer in vector. You want to stay in the same lattice to do this because you want to pull off these digits. In some cases, there are situations where you sort of need more digits than you want because having enough or covering all the residue classes is not enough. But there's this interesting research going on in this, and I don't completely understand all of it. But it's the same idea as before. If you want to do representing, you take your number, subtract off a good digit, and divide through, and that's pulling off the least significant digit of the expansion. So in this particular case, if I want to represent 1835, I figure out the good digit, subtract it off, multiply by m inverse, and I get a new integer 410, and I just keep repeating. And reading backwards, this will be my integer representation. I mean, strange digits, but there's nothing to say digits had to be nice integers. So I could have the digits 0, 1, 0, 0, minus 0, 1, and 0, 1. That's my representation of the integer 1835. If m is expansive, then a necessary condition for all numbers to be representable is the digit set is at least as large as the determinant of the matrix. And you sort of get this by the determinant of matrix determines the size of how big the lattice is, and you need a representation for each of the residue classes in the lattice. There's many results known, and many results known if it's an expansive matrix, but some of the terms are rational instead of integer. There's lots of stuff known on this, just not by me. Non-expansive matrices. So we looked at the expansive matrices, said, well, what happens if we cheat and just look at a Jordan block? It's definitely non-expansive. Every single eigenvalue is 1. It has advantages and disadvantages. The major disadvantage is if I invert this, it's still an integer matrix. So the fractional parts are absolutely useless. Fractional parts are still going to stay in the integers. But I did this work with, so Thomas Varva was a postdoc and Joshua Caldwell was an American equivalent to REU. It's a USRA in Canada. It's an undergraduate research thing. And it was a strange thing because the research was done in the middle of hard lockdown, but I was allowed to hire him and we did everything by Zoom. I did not meet him until about a term or two later when he was on campus and I was giving a talk about it. So it's weird to meet people after the research. But we did give a complete description if we had a Jordan block of dimension 2 of what digit sets work that give you everything that's representable. So one thing that we're not quite sure, well, if it's a Jordan block of size 2, 3, or 4, then there is a digit set that works of size 2 where you can represent everything. And it's easy to see that that's the minimal size of a digit set you can get, and we can achieve it. For the digits, for n greater than 4, we can find a digit set of size 3 that works, but we cannot prove 3 is minimal. It is possible there's a size 2 that works, we just don't know how to find it. And we did some investigations into bases similar to Jordan blocks, which is different than Jordan blocks in ways that you wouldn't expect. Topology. Here's where I deviate completely from everything I've done before, but have more pretty pictures. So it's the same idea. I'm going to have a matrix space, but now I'm going to look at the fractional parts. And this is sort of related to the dragging curve earlier. So look at the fractional parts, and I'm going to divide this into 4 cases. One is the complex, and the digits I'm always going to use is -1, or those are the digits that I'm using. I guess I use a different one for the Jordan block at the end. And what I want to look at is, what do the fractional parts look like? What is the topology of this fractional set? Like we saw in the complex case, it was a fractal, but it was a fractal that had a nice closed interior, and it had interior, and there's stuff going on. What happens in this case? So, for example, in the complex case, if I used base, the 1.1, 1.2, and so on, I get that object there on the left. That is not, it doesn't have any interior points. It's actually totally disconnected. On the other hand, for the next complex case, that is not totally disconnected. It is a completely path-connected set. I think it has interior, but I honestly can't remember. But there's questions about the topology of what the integers are. And here I should explain what the red and the blue part are. The red is the thing where the very first digit of the fractional numbers was -1, -1, and blue is where the very first digit was 1, 1. So I'm sort of dividing it into 2 cases. So everything here is totally disconnected. This actually means everything that is representable has a unique representation. Here, it is not totally disconnected. There are some serious overlaps. So this means that there's a number of things here that have more than one representation. So different matrix, same sort of examples. Here, again, totally disconnected. Here, it has interior. It's not obvious because I've got things that sort of look point-like here, but it is actually totally connected as well. And you can do this for all this sort of matrices. Totally disconnected on the left, really nicely connected on the right with interior. Totally disconnected on the left, nicely connected on the right with interior. And the question is, what happens if I fiddle with these parameters? For what parameters do these things have interior? For what parameters are these things connected? And then you get if M is the set of fractional representations, when is it connected, simply connected, disconnected? When do you contain interior? When do you contain a neighborhood of 0? Turns out the second question is answerable. The first question is only really answerable if you can answer the second. So there are cases where it's going to have interior, but 0 is not going to be in the interior, and we don't know how to prove it has interior. It just looks like it. And what can be said about the points with unique representation? So this is, what is it? So the matrices, parameters are done wrong here. So this is actually at the point 1/2, 1/2. So think of this as 2, 2 if I think about the original matrix. So everything here is totally disconnected. In fact, everything in this orange part is disconnected. Everything in this yellow part is disconnected, but we had to do more work to show it's disconnected. Everything in this sort of bluey thing here is disconnected, but we had to do even more work to show it's disconnected. And everything in the white part, we have no idea what's going on. Actually, that's not quite true. We know everything in that light blue is totally connected, and we know everything here. I've done it even more iterations, so you get a lot more detail. Everything on the bottom part, totally disconnected. It's a parameter space where everything's totally disconnected. Everything in the top, totally connected. Everything in the white, fair game, no one knows what's going on there. Moving on to the last topic with about, I timed this well. Okay. Last one, this is something that has a really long history called beta expansions. So this is what happens if I take base pi or base golden ratio, but I use digits that are nice integers. And as before, I mean, you can just represent a fractional number and lots of weird things happen. For example, I mean, in base 10, 1 can be represented as 0.999. Base 2, 1 can be represented as 111. Base golden ratio, we actually have a countable number of ways of representing 1. So we have 1 equals 1 over golden ratio plus 1 over golden ratio squared. But if I see 1 over golden ratio squared, I can replace that with 1 over golden ratio cubed and 1 over golden ratio 4. So every time I see one of these things, I can just sort of shift it over, take this 4, shift it over, and I keep doing this, and you actually get a countable number of ways to represent 1. If I'm going to use base golden ratio, there are actually numbers that actually have an uncountable number of representations. So sometimes you have a countable number, sometimes you have a finite number, sometimes you have an uncountable number, sometimes you have a unique number. Weird stuff happens. So if beta is an integer, there's exactly one beta expansion of 1, or beta expansion of 1. If it's a golden ratio, we have an infinite many, and an old result in 94 that said pick any n you want. Any finite number, or countable or uncountable, I can find you a base where 1 has exactly that many representations. So you can do weird stuff. If you've got more than 1 representation, you can say, well, you just sort of order them lexicographically. Say the largest lexicographically is greedy, lowest, smallest is lazy, and you actually can sort of sort these things. And so golden ratio, I've got a greedy expansion of 0.11, lazy expansion of 0.0111 repeating. Both of these are perfectly fine representations of 1. These studied back in 57. I think Perry did a bunch of stuff on it as well in the early 60s. And a lot of work on this. I'm going to gloss over this because I want to get to the results. I don't care about that stuff. So the study was done of univoque piezo numbers, or piezo numbers. Piezo is just a special type of algebraic number where everything nice happens. And it's univoque if there's exactly 1 representation 1. So we did a classification of all of those. Mason Panju was a bizarrely bright undergraduate student. I hired him for 4 months to do research. He got 2 papers out of it. I wish I could do that in 4 months. I definitely wish my grad students could do it with 4 months. And then he went into stats. But, oh, he'll be great in stats. So he just did he just completely described all the greedy expansions of a particular subclass of piezo numbers and just said, here's what they all are. And there's a lot of stuff there. And David Boyd started some work on beta expansions of Salem numbers, which is another type of algebraic integers, and had another undergraduate who continued this work. This one is a better direction. He started as an engineer, did a USRA, and now he's a grad student in math at UBC. So I lost 1 to math, I gained 1 to math. Net sum 0. That's everything.